Alright, so this unit, the periodic table, is a little more content-based, remembering a bunch of little facts kind of a unit. And here I'm just going to run through the gist of the major topics: table properties, group properties, types of elements, metals, nonmetals, metalloids, and some of the key trends that we're going to go through, and a little bit about predicting compounds. And hopefully this will help you guys. Okay, so we're going to start with table properties, and here I'm going to show you a periodic table. Here's some basic facts about it. So all of the elements are arranged into three different categories: metals, metalloids, and nonmetals. Metals make up the majority of the table. They're about 2/3 of the elements are metals. Next, you can find elements found in all three phases of matter: solids, liquids, and gases. The only thing you have to really remember is that only mercury and bromine are the only elements that are found as liquids in their natural state. A big thing to remember is that elements of the same group have similar chemical properties and the number of valence electrons. So if you look in your periodic table in the Regents reference table, you're able to see that those that share the same vertical column have the same number of valence electrons in their configuration. And also elements of the same period have the same energy level shell, so they fill up the same number of energy levels. And basically, groups and periods, what are the difference? Groups are the vertical columns that go up and down, and periods are the ones that go left to right across the table. Okay, same group, same number of valence electrons, same period, same number of energy level shells. Next thing we're going to talk about are the types of elements: metals, nonmetals, and metalloids. Metals make up most of the periodic table. They are shiny, they're bendable, they make good conductors, and they're likely to lose electrons and form cations. And they're located on the left side of the table, groups 1 through 12. Nonmetals, on the other hand, are not as shiny. They're dull, they're poor conductors, they're brittle, they kind of break apart easily, and they're more likely to gain electrons to form anions, and they're on the right side of the table. A fusion of both of these types are called the metalloids. They have both metal and nonmetal traits. They're located along the zigzag line on the right side of the periodic table, and some are borderline metalloid. So if you notice, those that border the zigzag line may or may not be considered metalloids. They may be leaned towards one end of the metallic spectrum. Okay, now this next section will cover each of the group properties: groups 1, 2, 3 through 12, 17, and group 18. Just about group 1, they're called the alkali metals. Group 2, the alkaline earth metals. 3 to 12 are the transition metals. Group 17 are the halogens. Group 18 are the noble gases. Okay, big important things is that the group numbers also kind of give you a hint as to their number of valence electrons, except 13 through 18, you kind of take that single digit number. Group 17, the halogens would have 7 valence electrons, and group 18 will have 8 valence electrons. What's important to know is that about group 17, they are diatomic, so that means 2 atoms together. So if you see that little drawing of 2 little circles molded together, that means they're diatomic, they're together. A good word to remember is Honkobriff. If you check that out, those list the elements that are considered diatomic. Honkobriff. Not all of them are halogens, by the way. Group 18 noble gases, they're the most stable elements because they have a full valence shell of 8 electrons. They don't want to react because they're very stable. They're happy, strong, independent atoms. They don't need a man. Okay, now we're finally getting into the periodic trends, and we'll start with the atomic radius trend. So we're referring to the size of the atoms. And let's start with sodium, which is a common cation. They lose electrons. So they start with a few valence electrons, and they lose those valence electrons to become a positive ion, so that it becomes smaller and more stable for them. So here we could see that the atom itself is actually bigger than the cation because they lose that extra energy level shell to go back down to 8. And as opposed to that, we have fluorine, which is a common nonmetal that makes anions, and so they want to gain electrons, and when they do, they become anions and they fill up their shell. and so they become just slightly bigger filling out. So as a result, we're able to see that anions are typically bigger than, well, not typically, they're really technically bigger than their stable at neutral atom state. And then from there we can get a sort of idea of how the atomic radius trend falls on the periodic table. So as you go down a group, you're adding on more and more energy level shells, and the more shells you have, the bigger that radius gets, so it increases going down the group. Now across a period, we're thinking about the pull between the protons and the electrons. So because they're opposite charges, they're pulling on each other. And so the more protons you add on, the more of a stronger pull these protons will have on these electrons. And that happens as you go across the period from left to right. And if all else fails, you're still unsure how these trends go, use table S. They give you the exact values of the atomic radius of each element. And if that, just remember the key ideas that atoms are bigger than cations and anions are bigger than the atoms. Okay, the next trend we're going to look at is electronegativity trend. And let's start with electronegativity, what it is. And it's the tendency to attract electrons from another atom. So the higher that is, the more likely it's going to attract electrons. That's going to have a stronger pull. If you look at this little cartoon here, electronegativity, they want to attack atoms for their electrons. So here you have a vicious fluorine atom with a sword saying, I want your electrons, because they really want those electrons. And if you look on table S, you'll see that fluorine has the highest electronegativity value of 4.0. And if you search for the lowest, you'll see that francium has the lowest at 0.7. And on this periodic table, francium's all the way out towards to the bottom left. And then fluorine is closer to the top right, sorry. And as you go towards that direction, you'll see that increase of electronegativity. Going down the group, they'll have lower electronegativity, and as you go across the period left to right, you'll see that increase. And here's some notes about why fluorine has the highest and francium has the lowest. Fluorine is a nonmetal, it's a halogen, and it really wants to get those electrons, so that's why they have a strong electronegativity. You want to attract them. And francium, it's a metal. It doesn't want to gain electrons. It wants to lose it, most likely. So that's why they don't want to give it up. I mean, they don't want to take more. It's better to lose one than to gain 7. And if all else fails again, always check table S for the exact values. Okay, ionization energy is next. And ionization energy is the energy required to remove a valence electron from an atom. And so if you have a high ionization energy, you want to keep your electrons, and it's going to be hard for other atoms to remove it. Whereas those with a low ionization energy, they want to lose electrons, so it's much easier to remove them. If you check out this little cartoon, you have a neon atom with its full 8 electron shell. And you see, here's a ionization energy. They really don't want to give up their electrons because they're very stable. So they're going to have that high ionization energy shield. So that's my little analogy. Electronegativity sword and the high ionization energy shield. So the shield really prevents others from taking, whereas the sword, it kind of helps with attracting. That's my little analogy. Okay, now let's take a look. Helium has the highest ionization energy with 2,372. It's a noble gas, so it doesn't want to give it up. It really wants to keep those electrons. Whereas cesium has the lowest. It's a metal. It has 1 valence electron, so it really wants to give it up so that it can reach that 8 valence electron shell. Okay. And if you look down the group, it decreases, and going left to right, it increases ionization energy. Now the last topic I'm going to talk about is predicting compounds, and this is a little more skill based. So here's a strategy I like to use, that I use with my class in order to be able to predict compounds. So here, first thing you want to do is identify the group number decide if it's a metal or non-metal, lose or gain electrons, how many, and what is the total exchange. Because what's important to see here is that one atom is going to lose electrons and then the other is going to gain that same number back. So there's a complete exchange. So if you give up 2, that other atom is going to gain it too, gain those 2 electrons. And let's take a look at an example, X2O. And we had to figure out what element is X, or what could it be. And so this is the way I do it. I break it up, X and O. And then we could go by the series of questions, identify its group number. We'll start with O. It's group 16. It's a nonmetal. It gains electrons. And oxygen in particular, it wants to gain 2 electrons to fill its shell. And in our problem example X2O, we have only 1 oxygen. So there's 2 electrons that needs to be exchanged. On the other side, we got to set that equal to 2 electrons being exchanged, because one atom is going to give it up, the other is going to gain it. And in our problem, we have 2 x's. So how many electrons does each x have to give up? So if we have a total of 2 electrons and 2 x's, each x is going to give up 1 electron. So we work our way backwards, divided by 2, because there are 2 x's. And so we've established it's going to lose electrons because oxygen is going to gain it. X is a metal, and it has to be in group 1. So let's look at our potential answers. Those in group 1 could be hydrogen, sodium, potassium, rubidium, cesium, francium. These are all potential answers for our problem. This is hypothetical, not realistic, just so you know. Now, in the event that we have transition metals, you want to look out for them. So you're going to check your periodic table on the reference sheets and see their oxidation states. If it also comes out to a +1, then it could also be a transition metal and not necessarily those in group 1. Same holds if it's a +2, then it could be a transition metal, or group 2, +3, group 13, or transition metal, etc. So keep a lookout for those transition metals if possible. Okay, so that brings us to the end of this video. Hope that was pretty helpful in some way. The protecting compounds topic is a little tough unless you have more examples to work and practice with. Other than that, the periodic trends might also be a tricky topic, but please remember you could always use table S to look up those values. In terms of the other things, just remember the little things. And other than that, this has been a pretty straightforward topic. I hope it's been helpful for you guys, and good luck tomorrow.